Exercise 10a should ring a bell because it's tangents and normals, and we've done this already, just not with trig functions. So where you'll be picking up 10a is question 9 and question 13, which are the ones that will involve trig. Okay, so the way we do tangents and normals is, so we want the equation of the tangent of the curve with this equation at the point x equals pi on 3. So basically what we're doing is we've got this sine function here, and at pi on 3, okay, which is roughly here, if you imagine a tangent drawn there, we want to get the equation of that line. So let's go about our business and do it. So to do it, what we need to do is work out the gradient at this point, which is the instantaneous rate of change. So we need to get dy dx. Okay, and dy dx is cosine x as per the formula sheet. Alright, so then we're going to go sub x equals pi on 3. So we're going to go cosine of pi on 3. What is the cosine of pi on 3? That is a half. Cosine of pi on 3 is a half. So that means m tangent, the gradient of the tangent, is going to be a half for this function. Now what we're going to use is this formula here, y take y1 equals m, x take x1. So recall that we need the gradient and we need 1 point. So the point we're going to use is pi on 3, and then we're going to pop pi on 3 to find out what the original y value is. So that's the sine of pi on 3. So that's going to be, knowing your exact values, root 3 on 2. Alright, so let's go ahead and go y take root 3 on 2 equals m, which is a half, x take pi on 3. Alrighty, so what we'll do is just get this into y equals mx plus c form. So we'll go y equals, so we're going to expand this right hand side, which is x on 2, take away pi on 6 plus this value here, root 3 on 2. Right, and there's the equation of our line. So it's got a gradient of a half and a y-intercept of whatever this value approximates to, but exactly negative pi on 6 plus root 3 on 2. Alright, and so that is enough to get you going on that. And just recall that if m tangent is 1 on 2, then m normal will be negative 2. It's the negative reciprocal of this. Again, nothing changes from what we've been doing, but I'm sure in these two questions there's probably the requirement to find the equation of the normal as well. It's also pretty easy to do on Mathematica. Have a look at my notebook from topic 4C, I think it is, and there's 2 commands there that will allow you to do that for the tangent or normal, given that these questions here are increasingly a 1-mark problem on the exam. Alrighty, so on to rates of change. So the depth of water, x meters, in a tidal river t hours after midnight is given by this function here. Find the rate at which the depth is changing at 4 AM exactly and 2 PM exactly. Alright, so when we're finding the rate at exactly a point, that means we need the derivative. So to work out the rate at which the depth is changing at 4 AM, we're going to say x of, now t is hours after midnight, so 4 AM is 4 hours after midnight. So we're going to do x dash 4. Okay, so into the derivative we'll pop 4. Alright, this could probably be done quite easily with or by hand, but let's just use Mathematica to do it. So f x equals 3 sin brackets times x all on 12 plus 1. I think, do I have to use the square brackets there? I think I do. F of 2. Okay, so what we'll do is f of 4 now, which, no, we'll do f dash 4. Oh, come on. And the answer is pi on 8. All right, and the depth of water in meters, hours after midnight. So this is meters per hour. So it's increasing at a rate of pi on 8 meters per hour at exactly that point. All right, let's do 2 p.m. So 2 p.m. Is going to be 14 hours after midnight. So x dash 14. So we'll go over here and do f dash 14. Is it going to be the same? No, it's not. There it is there. Negative root 3 pi on 8. And again, the unit is meters per hour. So obviously you can tell that the rate is negative in this case. All right. Find the average rate of change of the depth of water over the first 6 hours. So m average, so the average rate of change is going to be x of 6 take away x of 0. So this is y2 take y1 over x2 take x1, which is 6 take away 0. So for this one, we've got the, I'll just bring up palettes. Not that one. This one, we're going to do f of 6 take away f of 0 all over 6, and it's a half. Alright, so again, just using function notation as much as possible in your working out, and then, yeah, just get Mathematica to do the hard work for you. Alright, the height above the ground, h meters of the central point of the path of a skipping rope as it's being turned by m as she works out in the gym is found by this equation here, where t is the number of seconds after the skipping rope has begun to turn from its starting position, resting on the ground. During the skipping activity, the maximum height of the rope reaches 1.8 meters and takes 2 seconds. Okay. So what's going to happen basically is, all right, this is the person with the skipping rope. Right, and the skipping rope gets swung around her head, all right? And if it's starting at the ground level, that's 0, then its maximum height is going to be 1.8. Okay, so 1.8 off the ground, which means the midline is going to be 0.9. Okay, so let's start writing this out. So we've got, and it's got to be cosine as well. That's interesting. So cosine, so what it's going to happen is its standard cosine is going to look like that. We've got to invert the standard cosine so it looks like that. So what's going to happen is skipping rope starts on the ground, starts to turn, goes to its maximum height and goes back down again. And that's got to happen in 2, that's 1.8, and the mean line is 0.9. Okay, so we can write out this function now quite quickly. So it's going to be h of t equals, so the amplitude is going to be 0.9 because it's 0.9 to 1.8, and it has to be negative to invert the cosine. So it's negative 0.9 cosine, don't know my n value at the moment, I'm just going to leave that, plus, so it gets elevated up to 0.9. Now the n is the period, so we've got a standard cosine period of 2 pi over n, and we want the period to be 2. So that's going to be n to there and 2 to there. 2 pi on 2 equals n is pi. So h of t equals negative 0.9 cosine pi t plus plus 0.9. All right. State the time at which the maximum rate of change in the height of the rope occurs. So when is the rate of change at its largest? Okay. So this is pretty tough here. So what we're going to do is, so there's my original function. So originally it's going to look like this. All right. And when is it changing at its most? So where it's going to be changing at its most is these two sections here. This is when it climbs or drops at the fastest possible rate. Okay, so it's climbing there at the fastest rate and dropping there at the fastest rate. And that's where the maximum rates of change are going to occur. Okay, so there's a couple of ways of doing this really. Is the first way we can graph or imagine what the derivative function will look like. Okay. So we'll get h dash t equals. So let's go ahead and start this up on Mathematica. So get rid of that. So I'm going to go h t negative 0.9 cosine pi times t plus 0.9. Let's have a look at it. Okay, that looks good. Okay, so what's going to happen is, what we're going to get, let's get the rate of change function. So we'll go h dash t, and it's giving us that. Now I think, let me just pause this to remember the command to give me the fraction version of this. Please pause. Alright, so back after a bit of fiddling around here. So I did get the derivative. So here's h dash t, and I did get it out in fraction form rather than decimal approximation form. The way I did that was actually go back to the original function and write 0.9 as 9/10 and plus 0.9 as 9/10 as well. And if the input or the original function is a fraction, then the output will be a fraction. I'm sure there's a way to do it to get it to happen automatically, but I couldn't work it out and I'm running out of time. So here's h dash t. Right, now what we're going to do is have a look at the derivative. So let's plot it. Alright, so here's the rate of change function. And what you can see is we're looking for the maximum rate of change. Okay, the highest rate of change. You'll notice that the highest rate of change happens here. So this is the first 2 seconds. Let's shrink down the range, domain rather. So 0 to 2. So this is just one skip, if you like. All right. So what happens is it's got 0 rate of change initially. Okay. Because why? Because it's on the ground. Okay. And it goes up. We've got our maximum rate of change. Okay. So what we've got is it's this point here, and then we're at the top. And then what's going to happen is it's going to come back down again. Okay. So coming back down. And we've also got this maximum rate of change here, okay, at this point here. So that's actually this point here, all right? This point here is this point here, which is also the maximum rate of change. It just so happens that the rate of change here is negative and the rate of change over here is positive. That's fine, okay? When we're talking about rates of change, we're talking about the magnitude. It doesn't matter whether it's positive or negative. They're both exactly the same maximum rate of change, even though this is the smallest value. So how are we going to work out this? This is the maximum value of the derivative function, or the minimum value of the derivative function. So the way we're going to do this is we're going to do h double dash t. We're going to say when is the second derivative, i.e. when is the derivative of the derivative equal to 0. And it's going to be at this point here, which we can see is 0.5 and 1.5. So I'm going to set the second derivative to 0 and ask it to solve for me. Okay, so what am I going to do? I'm going to solve h double dash t equals 0. I'm going to restrict the domain, otherwise it's going to give me a general solution. Two, close that. This will be a miracle if I get this right for t. Yes. Okay, what's wrong with it? I think the comma. So fussy. Okay, so t equals a half, t equals 3 on 2. Okay, so the time at which the maximum rate of change in the height of the skipping rope occurs. So the first time is going to be at a half, the second time is going to be at 3 on 2. Now, interestingly, it doesn't tell us how long she actually skips for, m. So what we might have to assume is actually, unfortunately, that this is a general solution. Okay, so the first time it's going to be t equals a half, and then it's going to be every plus 2 after that. It's going to be exactly the same. So we're going to put a plus 2, which is the period, n, and same with this solution here. We're going to have a plus 2n on this, where n is an element of, we'll say z. We'll only take the positive ones, okay, because we can't go back in time. So she starts skipping, and we assume, because it doesn't really say how long she skips for, that this goes to positive infinity. Okay, so we're just going to keep banging out solutions until, well, infinity in this case, but because we're not told how long she does it for. So yeah, pretty tough question, that one there. Right, and the exercise, where's the exercise? 10b. Questions somewhere here. (10b). So exercise 10b, Q, 9 and 10. 10b, Q, 9 and 10. All right, so get those done, and I'll catch you guys on Tuesday. All right, so this one here, 10b, Q, 9 and 10. All right.